Three, two, one. All right. Welcome to another 2070 video, the online section of linear algebra. All right, and today we're gonna do more of a deep dive into the world of matrices and talk about some of the operations we can perform on them. All right, so let's set up with some notation here that's going to help us out. So given a matrix, it has rows, it has columns, and if I want to talk about the entry that's in the jth row and the jth column, the notation that we will use is A sub jk, like that. Note I place a comma here. That is not 100% standard. Sometimes people will drop the comma. And for the most part, right, that's pretty clear notationally. But when you've got like J is 10 and K is 11, it can start getting a little confusing. So I like to be overly notative here to ensure clarity, but you can use whatever notation you want. Also worth noting that this is not 100% standard to represent the jth, kth entry in a matrix, but it's a notation I'll use. And one of the benefits of this is that it lets us very precisely describe the various algebraic maneuvers we can apply to matrices. We've already talked about multiplying a vector by a matrix, but of course we can take a matrix and modify it using itself and matrices. So in particular, scaling a matrix is a matrix defined as alpha A, where the jkth entry is the jkth entry scaled by alpha. So scaling a matrix works the way you think it should. You scale it by multiplying each entry by the scalar you're looking at. And the sum of two entries is what you think it should be as well. The sum of two matrices is done entry-wise. So to visually get a grip on these, so if we have a matrix A, here's 1, 1, 2, 2, 1, and a matrix B, -3, -2, 4, and 2, I can add them, and adding them goes the way you think it should. I add up the corresponding entries accordingly. Subtracting them also works the way you want, and again, remember, there's no such thing as subtraction. There is adding by a negative. Multiplying a matrix by 2, and then, right, so these matrix operations here behave pretty much exactly as expected. Right, so scaling and adding matrices is done entry-wise, and as we see here in these processes here, right, goes the way you think it should. No, nothing weird or fancy or what. It's just you scale the matrix, you multiply the entries, you add matrices, you add the entries. And again, as we mentioned, we can subtract, where what you're doing is really adding by scaling it by -1 first. All right, so that being said, let's get to the real money for today, the big thing for today, which is multiplying two matrices. So we've already seen that given a matrix and a vector, I can multiply the vector by the matrix, and that is formed by scaling the columns of the matrix and adding them up. Now, if I have two matrices and I want to multiply them together, it's going to be a little bit more involved, but note immediately we kind of see a very familiar format going on here. All right. Now, before, we had an m by n matrix, and when I can multiply by a vector, the vector needed to be an Rn. So my matrix, there we see the n needs to match. So given a matrix A, that's a m by n, and a matrix B, that's an n by p, then the product is a m by p matrix, and the jkth entry is defined as follows. We lock down the jth row of A, the kth row of the kth column of B, and then I pair up, multiply, and add up. All right. Now, right off the bat, we kind of see again that similar format of things are kind of getting scaled and added up. But here, right, we have two matrices going on, so right, it's not exactly what we saw before, but the general format of a linear combo here. And hey, our linear equations we like working with look very similar to this. So, all right. Now, this is all well and good, but an actual example here is going to give you a very good idea of how this goes down. So here, note I have a 3 by 2 matrix, and here I have a 2 by 2. So the dimensions line up, which means I'm allowed to multiply them. And here we see why we need the dimensions to sort of work out. And with this all sprawled out here, you can kind of see visually what's going on. The 1, 1 entry right here is found by taking the first row of A and the first column of B, matching the entries, multiplying, and adding them up. All right, likewise here, the second row of A times B the second row of A, the first column, and then the second column, matching and multiplying and adding up. And so on and so forth. So if I want the 3 by 2 entry, I go to the third row of A, pair it with the corresponding column of B, multiply the entries, and then add them up. All right, nice. And then there we see that the dimensional thing needs to line up correctly. The number of the entries in the row of A need to match the entries in the column of B, hence why I need the number of columns of A and the number of rows of B to line up. Right, so now for this particular matrix, I have A times B defined, but B times A cannot be computed because it's a 2 by 2 multiplying a 3 by 2. So if you're going to try to match this row to this column, well, this column is a third thing that this row does not have, so it can't multiply up and then add up. All right, so hey, there we go. That's how you multiply two matrices. Now, on your own, verify that this really did not change how things were done. If B was an n by 1 vector, note that we would end up with the same thing. So this just sort of extends our definition from the case where B is a vector to allow for any matrix multiplication. And as we will see in the coming videos, we can use matrix multiplication for a wide variety of things, and it has a lot of really nice properties and some interesting theorems. Now, the first thing we want to discuss here is the weird things matrix multiplication does. And this one comes from our own professor of mathematics here in the math department at Iowa State, Professor Joey Iverson. So in the before times, me and him were teaching this class 207, and we were talking about matrix multiplication, and he always liked talking about the three weird things that matrix multiplication does. So the first weird thing it does, which we've kind of already seen, is that it's not commutative. A times B and B times A are not necessarily going to equal each other. Now, that's really obvious when A times B is defined and B times A isn't, as we just saw, but it's possible that both A times B and B times A are defined, but when you do the multiplication, you get different things. So matrix multiplication failing to be commutative is probably one of the most famous examples of a non-commutative operation that is of incredible importance. Another one that you may encountered and notice is not commutative is function composition. I wonder if matrix multiplication is really just function composition in disguise. Like, I don't know, the linear mapping yields a matrix. Oh, boy. Oh, boy. All right. So it's not commutative. That's the first weird thing it does. The next weird thing is that you can multiply two non-zero matrices and get the zero matrix. Right, and that one immediately goes against everything you normally think about when it comes to multiplication. Right, if I told you A times B is equal to 0, the first thing your brain does is A is 0 or B is 0. And as we see with matrices, that is not the case. So very important to keep that in mind, that matrix multiplication can multiply out and give you 0, but the things you used were non-zero. Very bizarre. And related to this is that there is no hope for cancellation, meaning that I can have A times B and A times C, and they can equal each other, but B and C were incredibly different matrices. So I would love to cancel matrix equations, but it turns out I have to be very careful about that. And we'll talk about that in the next video when I'm actually allowed to do cancellation. And I wonder if you heard that or not. I think I got an email or something, or some sort of alert. Anyway. Sweet. So those are the patented Professor Iverson weird things about matrix mult. Not commutative. You can multiply and get 0, and you can't cancel. So the A times B is not B times A. A times B can equal 0, and A and B are not 0. And AB equaling AC does not tell me B is C. So the things we sort of immediately take for granted about multiplication, they're out the window. That being said, though, there are things that are true. It is associative, and this is sort of the subtle property. Associative operations in mathematics we kind of sweep this one under the rug a lot. But it is very important to note that if I multiply up a whole bunch of matrices, it doesn't matter where I slap my parentheses, I will always get the same computation. Now, in your math life, you've most likely never ran into anything not associative, but if you've taken Calc 3, cross product is a very famous example of a non-associative operation. But for the most part, most operations in mathematics are associative, so we usually don't need to get too sweaty about them. But, all right. So we do have the associativity. We do have a distributivity. If I multiply a sum, then the A goes across the board. And note, we also need to worry about multiplying on the right versus the left, because we know we can't commute the matrix multiplication, so we need to know that both of these work. And fortunately, they do. Next up, and this is my favorite. This is my favorite matrix property. If you scale a product, you can put the scalar on the first matrix or the second matrix. And the fact that this one lets us pull scalars out of the middle of a multiplication, there's some stuff you could do with this. There's a very famous matrix equation where you have to pull out this scalar, and it's a neat little thing. It's called the inversion lemma, or some version of that. And there's this moment where you got to pull a scalar out of the middle, and I remember when I first started learning it, I was like, "Oh, that's the coolest thing." So this one's my favorite. I think this is the coolest thing. Maybe you don't, but this is neat to me. All right. Well, while we're talking about some nice properties, let's remember our friend the identity matrix, the matrix of 1 on the diagonals and zeros elsewhere. All right, so the matrix whose columns are the standard basis elements. We called it the identity matrix, and now we're going to learn why. Because if I take a matrix and multiply by the identity matrix, if I were to look at the JK entry, note it would be this, but note the i's are going to zero out when the h here that's running from 1 to n is anything other than k. And when it is k, oh look, I just get the JK entry of a. So in other words, a times I and a have the same JK entry, meaning they have to be the same matrix. So multiplying on the right by the identity matrix doesn't do anything. And similarly, multiplying on the left doesn't do anything. So the identity matrix is the identity for matrix multiplication, hence its name. Now we finally know why we called it the identity matrix. So that's good to know that when we multiply matrices, I do have an option to multiply and not do anything. And that means if I've got a way of multiplying and not doing anything, I have a method of talking about undoing a matrix multiplication. And we'll get into that in the next video. All right, but let's wrap things up today with a very matrix-specific maneuver. So while matrix multiplication obviously was sort of very matrix-dependent and defined on it, I did kind of let slip that it's really actually a function composition in disguise. So there's a little thing going on there. But let's talk about something that's really matrix, and that's the notion of transposing. So the jkth entry of a transpose is the kth jth entry of the original. So in other words, take a matrix, turn the rows into the columns, and the columns into the rows. Right? You need to have something with rows and columns to perform this operation, so you need a matrix. This is a matrix-only maneuver. That's a big, bold claim. There's other things you can transpose, but just the general idea of swap the rows and the columns, well, you need something with rows and columns in order to be able to do that, so truly a matrix maneuver. Right, and here we see a nice precise definition for it. However, visually speaking, it does this. Column 1 becomes row 1, column 2 becomes row 2, or the other way around, row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3. Either way works. Nice. And transposing satisfies some nice properties. So if you transpose a scaled matrix, you get the scaled transpose. If you transpose a sum, you get the sum of the transposes. An interesting one is the transpose of a product is the product of the transposi, but you got to do the order of the matrix multiplication in reverse. And that shouldn't be shocking because no transposing will change the dimensions of your matrix. It will swap the rows and the columns. So the only way that the multiplication can be defined is if you swap the order of it. And finally, a very interesting thing, if you transpose the transpose, you're back to normal. So that should be clear. If you swap the rows with the columns and then do it again, then you're back where you started. But this property here, we're applying a mapping twice, gets us back to the original. This is called an involution, and involutive things are very useful and frequently appear in mathematics. All right, cool. Now, at first glance, it seems like transposing is just like, yeah, you can do this, but you're going to be shocked at how often we end up using this and how powerful this ends up being. This is a great example of like a math thing that's just sort of like there's a clear mechanism that is being performed here, but the utilitarian, the utilization, whatever word I'm trying to use here, how this is used is not sort of immediately obvious. It's just right now seems like a pretty basic thing we can do. But I promise you, when we get the least squares, transposing is going to show up and it's going to save the day. All right, so that takes care of our first foray into some operations we can perform on our matrices. I'll see you in the next video where we'll talk about inverting matrix multiplication.